Limiting reagent problems. Let's say you have a reaction, A plus B goes to C. And you dump in a beaker so many grams of A, and you dump in so many grams of B, and what are the odds that you added the exact right amount of A and B so that there's no waste at all, that all of A and all of B reacted? Oh, that's never the case. There's always one or the others left over. In other words, either A is all going to react up first, or either B is going to react up first. But the point is, once one of those reactants is depleted, the reaction stops. You're not producing any more product. So these are called limiting reagent problems. So here's an analogy of a limiting reagent problem. We're going to make s'mores, and I like them with 9 marshmallows and 2 graham crackers and a whole chocolate bar, and I'll get 2 s'mores out of this. And you just break it in half. Okay, let's say all we brought camping were 18 graham crackers, 90 marshmallows, and 7 chocolate bars. So in theory, you don't lose anything, you don't drop anything. In theory, how many s'mores can you make? So what we're going to have to do is figure out how many s'mores you can make with 18 graham crackers, the 90 marshmallows, and the 7 chocolate bars. See how many s'mores you can make with each of those, and then just pick your smallest answer, right? So if we start with the 18 grams, right, we want to get to s'mores. Well, what's our mole bridge? We've got 2 grams for every 2 s'mores. So that's just 18 s'mores. If we had 90 marshmallows, how many s'mores can you get? Well, we have 9 marshmallows for every 2 s'mores. So what is that, 10, 20? 20 s'mores. We have 7 chocolate bars. How many s'mores can you get out of that? Well, for every 1 chocolate bar, you have 2 s'mores. So that would be 14 s'mores. So in theory, how many s'mores can you make? Well, you use up all the 18 graham crackers, you'll get 18 s'mores. If you use up all the marshmallows, you get 20. But we don't have enough graham crackers to make 20 s'mores. You see the problem? So what we're going to have to use is the chocolate bars. The chocolate bars are all going to get used up first, because once you make 14 s'mores, all the chocolate bars are gone. So 14 s'mores is all you can make, and it's all determined by those darn chocolate bars. So in theory, you can make 14 s'mores. Now some terminology. What's the limiting reagent? What determined that answer? Well, the chocolate bars did. So whenever they say, what's the limiting reagent, they're talking about the reactant. That's gone first. Right? Which reactant all reacts up first and determines the answer? It's the limiting reagent. It's always a reactant. Theoretically, how many extra marshmallows are there? So think about this. You're going to have 7 chocolate bars, and you're going to make 14 s'mores out of that. Well, you used up how many marshmallows? And once you figure out how many marshmallows you used up, just subtract that from 90. That's the game plan. So how do you figure out how many marshmallows you used up? Always use the limiting reagent, because you know that's the reactant that got used up first. So that's going to determine how many marshmallows are going to be used. That's going to determine how many graham crackers were used. That's going to determine how many s'mores were made. Okay? So we're going to start with the limiting reagent, 7 chocolate bars, and convert to marshmallows. And how many 1 chocolate bar for 9 marshmallows. 1 chocolate bar for 9 marshmallows. So 9 times 7 is 63. So 7 chocolate bars were used up. That means 63 marshmallows were used up. So the number of marshmallows that remain would be the original minus the amount that reacted, right? So we'd have 90 minus 63, which is 27 marshmallows are left over. Now you didn't have to use the limiting reagent to get the right answer here. You could have also used the amount of product. And what they call that, the amount of product that you got, they call that the theoretical yield. So in theory, how much product do you get? They call it the theoretical yield. So what is the theoretical yield of s'mores? Just 14. If 7 s'mores were actually made, so you drop some or something, right? What's the percent yield? So there's an equation for it. So my percent yield then is the actual 7 were made, 14 were in theory, times 100. So that's 50%. So my percent yield is 50%. My theoretical yield is 14 s'mores. So just some terminology to get used to. In the above reaction, 24.2 grams of ammonia is combined with 32.6 grams of oxygen. Determine the limiting reagent and theoretical yield in grams of production for water. So we're starting with 24.2 grams of ammonia and 32.6 grams of oxygen. Which one reacts up first? Well, let's do the same thing we did with the s'mores. Let's convert both of those to grams of water. And we will pick our smallest answer, right? And that'll be the theoretical yield. The one that gave the theoretical yield is the limiting reactant. Let's try it. So we have 24.2 grams of ammonia and 32.6 grams of oxygen. And we're going to convert both of those all the way to grams of water. So first we'll need molar mass, so we can use our mole bridge. Then the mole bridge, I want to end up in water. They want grams of water, so you need the molar mass of water. Same thing with the oxygen. I need to get it into moles of oxygen, mole bridge, and I want to end up in water, so that's on top, and then the molar mass of water. Okay, I'll just put in the numbers. In 1 mole of ammonia, I've got about 14.01 plus 3 times 1.01, about 17.04 grams of ammonia. I've got 6 moles of water for every 4 moles of ammonia, and every 1 mole of water, I've got 18 grams of water. The bottom one, 32 grams of oxygen and a mole of oxygen, 5 moles of oxygen for every 6 moles of water, and a mole of water, 18 grams. So let's see which one gives us the smallest answer. 24.2 divided by 17.04 times 6 divided by 4 times 18, about 38.3. And the other one, 32.6 divided by 32 times 6 divided by 5 times 18, about 22. So which one is my answer? It's the smallest one. I don't have enough oxygen to make that much water. I can only make this much water. So there's my theoretical yield. And then they said determine, and we should label these, because that's my theoretical yield. So that means that oxygen is my limiting reactant, or reagent, same thing. If the actual yield is 18 grams of water, find the percent yield. So if you take the actual all over the theoretical times 100, you get percent yield. So 18 divided by 22 times 100, about 82%. Let's try this next one. We have a reaction, and they say that I've got 30 grams of carbon disulfide. So I've got 30 grams of that compound, and I've got 35 grams of oxygen. So 35 grams of that compound. Okay. Which reactant remains unconsumed at the end of the reaction? So one of these is going to react up first, leaving the other one in excess. They want to know which one is in excess. Which one do I have extra of? Okay. Do you see a game plan? Let's just start with one of those reactants, I don't care which one, and convert it to the other reactant and see if we have enough, right? What I mean is, start with one of the reactants. I'm just going to start with the carbon disulfide. Let's convert it to grams of the other reactant, grams of oxygen, and see if we have enough. So first is molar mass, then mole bridge. You want to get into oxygen, and then molar mass of oxygen, because you want grams of oxygen. So in 1 mole of carbon disulfide, I've got 12.01 plus 2 times 32.066, about 76.14, and I've got 3 moles of oxygen for every 1 mole of carbon disulfide. And a mole of oxygen, about 32 grams. So 30 divided by 76.14 times 3 times 32, about 37.8. Okay, if 30 react, I need 37.8 grams of oxygen. How many grams of oxygen do I have? I only have 35. So that means oxygen must be the limiting reagent, right? It's all gone first. I have excess carbon disulfide. So which one remains unconsumed? Carbon disulfide. I have extra of it. Okay, it's the one that I'm going to have a lot left over. How many grams of each reactant remain at the end of the reaction? Well, the easiest one is going to be the limiting reagent. The limiting reagent always has 0 because it's all gone. Zero grams of oxygen. 0.0. Okay. The other one, we're going to have to calculate it, right? So start with the limiting reagent. Remember, use limiting reagent for all calculations. So we're going to use the limiting reagent to calculate the grams of carbon disulfide that reacted. Right? Then subtract from the original amount. Okay? So let's use the limiting reagent for all calculations. So let's start with the grams of oxygen. You've got 35 grams of oxygen. Too bad we didn't pick this one out in the first place. 35 grams of oxygen. We need to get it into moles of oxygen. Mole bridge. Molar mass. So that's going to be the grams of, since this is the grams of oxygen that reacted, that's our limiting reagent, that's going to be the grams of carbon disulfide that reacted. Okay? And we'll subtract that from our original amount. So in 1 mole of oxygen, I've got 32 grams. Carbon disulfide, I've got 1 mole of it for every 3 moles of oxygen. And the molar mass of carbon disulfide is 76.14. So 35 divided by 32 divided by 3 times 76.14, about 27.8. 27.8 grams of carbon disulfide reacted. So the amount left over is going to be the original, which is 30 minus 27.8. About 2.2. That's going to be the amount that's left over. Nitric acid manufactured in the Ostwald process. Here's the reaction. How many grams of nitric acid are produced in a mixture of 2.1 grams of nitrogen dioxide and 2.29 grams of water? So definitely a limiting reagent problem. We want to end up in grams of nitric acid. So let's just convert our amounts to grams of nitric acid and pick our smallest answer. And the other one is 2.29 grams of water. So molar mass. Mole bridge. Wrap up with molar mass again. Do the same for the other reactant. So in 1 mole of nitrogen dioxide, I've got 14.01 plus 32, 46.01. And I've got 2 moles of nitric acid for every 3 moles of nitrogen dioxide. Nitric acid's molar mass, 1.01. Nitric acid's molar mass, 1.01 for hydrogen, plus 14.01 for nitrogen, plus 3 times 16, about 63.02. 18 grams of water in a mole. I've got 1 mole of water for every 2 moles of nitric acid. And in a mole of nitric acid, 63.02 grams. So about 1.92 for the first one, and about 16 for the bottom one. How many grams of nitric acid? It's always your smallest answer. There it is. my theoretical yield of nitric acid, all 2.1 grams of nitrogen dioxide react, assuming. Okay, let's try this one. In a mixture of 42.1 grams of nitrogen dioxide, so if we clean this up, we've got 42.1 grams of nitrogen dioxide and 43.6 grams of water. Okay, how many grams of the excess reagent remain? So you remember how to do this? Now it's a whole new problem. So we don't know which reactant is the limiting reagent. They're just taking these amounts and dumping them in together. Okay, do you remember how we did it? We just picked one of them and we converted it to the other compound to see if we have enough. Okay, let's try it. So let's pick one of them. 42.1 grams of nitrogen dioxide. Let's convert it all the way to grams of water and see if we have enough. So we'll start with molar mass, mole bridge, my molar mass of nitrogen dioxide is 46.01, all right? And moles of water, I have 1 mole of water for every 3 moles of nitrogen dioxide. And my molar mass of water is about 18. So 42.1, I get about 5.49 grams of water. So if all of this react, that's all I need. If it all reacts, all I need is 5.5 grams of water. I've got 43.6 grams of water, right? So this nitrogen dioxide, it's all going to react first because I'm going to have a lot of water left over. All I need is 5.5 grams of water to react with all of this nitrogen dioxide. All I need is 5.5 grams. So there's going to be a lot of water left over. Okay, so how many grams of the excess reagent remain? I know that I have 5.49 grams of water reacted. How much did I have there originally? At 43.6. So just subtract them. 43.6 minus 5.49, I'll have 38.11 grams of water remain, assuming all of that nitrogen dioxide reacts. So in these problems, figure out what the limiting reagent is, and in general just use it for all calculations, whether you're talking about how many grams of another reactant are left over or how many grams of a product are being produced.